I want you to imagine, just for a second, looking at a simple photograph on your phone.
Right.
Like maybe it's a picture of that coffee mug sitting right there on your desk. Now imagine you could just reach your finger into the screen, apply a virtual push to the side of that mug, and literally watch the coffee realistically slosh over the rim.
And not just as some, pre-programmed cartoon animation,
Yeah, exactly.
but a real physical reaction,
Yeah.
complete with accurate shadows, lighting changes, and realistic liquid physics, all happening right there in real time.
It sounds like complete science fiction. I mean, today is March 12, 2026, and as incredible as video generation AI has gotten recently, it actually has this dirty little secret.
It really does.
It has absolutely no idea how gravity, mass, or physics actually work.
Yeah, it's a massive blind spot in the technology right now.
Hmm.
We have these models that can generate breathtaking, hyper-realistic clips, but at their core, they are basically just guessing where pixels should go.
Right, based on visual patterns they've seen before.
Exactly. They don't actually understand the physical rules of the universe.
Which brings us to the mission for today's deep dive. We're looking at a stack of notes and a groundbreaking new research paper outlining a system called RealWonder.
RealWonder, yeah.
And this is the first real-time system that actually allows you to apply 3D physical actions, so like forces, wind, or even robotic movements, to a single static image and instantly generate a video of the physical consequences.
It's a huge shift. We are looking at a transition from passively watching AI-generated video to actively interacting with a simulated world.
The journey of how they actually pulled this off is fascinating. So we are going to unpack how scientists finally taught an AI video generator to obey the laws of physics without actually forcing it to learn physics at all.
Which is such a clever workaround.
It is. But to appreciate why RealWonder is such a massive breakthrough, we first really need to understand why current top-tier video models completely fail when you ask them to follow basic physical laws.
Right, so if we look at the current landscape of video models, they operate entirely in two-dimensional screen space.
Okay.
So when you introduce a 3D force, say, a push from the left, the model has no structural understanding of how that force should propagate through the actual geometry of the scene.
The source material has a frankly hilarious example of this. The researchers set up a test with a photo of 3 persimmons, just stacked on top of each other.
Yeah, the persimmon problem.
Right. And then they asked baseline state-of-the-art models, specifically CogVideoX and Tora, to simulate what would happen if that stack was hit from both sides at the exact same time.
A very simple action and reaction scenario.
Yeah.
You apply a force, the object should react, but the baseline models completely fell apart.
Yeah, CogVideoX basically just gave up. It failed to generate any dynamic movement at all and just froze.
Typical.
But Tora was the really interesting failure because it completely violated object permanence.
Oh, totally.
When the imaginary hits landed, Tora actually melted 2 of the persimmons together into a single blob.
And then it just magically spawned a brand new persimmon out of thin air at the end of the clip.
Exactly. It's so weird.
But it perfectly highlights the exact limitation of pattern matching. The AI is trying to match the visual pattern of a hit or a movement based on its training data.
Right.
It has no underlying concept that a persimmon is a distinct physical entity with mass that, cannot simply merge and duplicate.
It reminds me of a lucid dream. Like everything looks hyper real, but then you try to read a clock or you drop an apple and suddenly the logic completely breaks.
That's a great analogy.
But hold on, let me push back on this a bit. If these companies have billions of dollars and massive supercomputers, why can't they just force-feed the AI a million YouTube videos of things falling over or being pushed until it just naturally learns how gravity and mass work?
Well, that is the exact bottleneck that researchers had to overcome. See, physical actions like forces and torques are continuous, high-dimensional, and unbounded.
Okay, what does that actually mean in the context of training an AI?
Think about how we usually train AI models. We use discrete tokens. We can tokenize words in text very easily, right? Like A, B, C.
Sure.
We can even tokenize discrete camera movements like pan left. But you cannot easily tokenize a 3D force that varies infinitely in magnitude, direction, and the exact point where it's applied.
Oh, I see.
Furthermore, if you look at a regular YouTube video of a tree falling, It is nearly impossible to infer the precise, invisible 3D forces that cause that motion.
Right, because you don't know the exact wind speed or the structural stress of the trunk.
Precisely. You can't actually see the force itself. You only see the visual result.
So the necessary action video training pairs, the data linking the exact invisible force to the visual outcome, they just simply don't exist.
Exactly. And you cannot train a model on data you do not have.
Okay, so if you cannot train video models on invisible forces, how did the RealWonder team get past this?
Well, since they couldn't teach the video AI physics directly, they decided not to.
Wait, what? They just gave up on teaching it physics?
Kind of. Instead, they use a traditional hard-coded physics simulator to act as an intermediate bridge between the user's physical action and the video generator.
Okay, let me try an analogy here. Let's say it's like having a master painter who has lived their entire life in a windowless room.
Okay, I like where this is going.
They can paint anything perfectly, but they have never actually seen the wind. You don't sit there and try to explain the complex mathematics of fluid dynamics and wind resistance to them.
Right, they wouldn't understand it anyway.
Exactly. Instead, you hand them a perfectly accurate but really crude stick figure sketch of a tree bending, and you just say, here, make this look photorealistic.
And to take that painter analogy one step further, the crude stick figure sketch the simulator hands over actually comes in two very specific layers.
Oh, really?
Yeah. The physics simulator is doing all the mathematical heavy lifting, computing the collision and the gravity, and it outputs two specific visual cues for the AI to follow. First, it generates something called optical flow.
Which is essentially a pixel-by-pixel map of where everything is moving.
Yes, think of it like a weather map. But instead of showing wind currents, it shows pixel velocities. It tells the AI, this specific group of pixels needs to move exactly 2 inches to the left.
Okay, got it. And what's the second layer?
The second visual cue is a coarse RGB preview.
The source material shows this preview, and man, it looks incredibly blocky.
Yeah, it is a crude 3D render of the scene. It's not pretty, but it shows the AI crucial structural changes that pure velocity cannot convey.
Like what?
For example, if a cup moves behind a book, that is an occlusion. The course preview shows the AI exactly how those objects overlap in 3D space.
Oh, so the AI never has to think about the math of a 3D force. It just looks at these visual instructions and paints the frames.
Exactly.
So how does a flat photo of my desk actually become a 3D simulation in the first place?
Because we are starting with a flat 2D input image, the first thing the system has to do is give that image depth. So it unprojects the 2D image into a 3D point cloud.
Like translating a flat painting into a swarm of dots hovering in 3D space.
Exactly. It estimates the depth and the geometry of the scene. But geometry alone isn't enough for physics. You also need to know what things are made of.
Right, because a block of butter behaves very differently than a block of concrete if you poke it.
Right. So RealWonder brings in a vision language model, or VLM, to act as a sort of material appraiser. It analyzes the objects in the scene and categorizes them into 6 types.
Which are?
Rigid, elastic, cloth, smoke, liquid, or granular.
Granular, like a sandcastle on a beach. And I imagine you could manually override this if you wanted to. Like, say the AI thinks a rock is rigid, but you want to see what happens if it behaves like Jell-O.
Oh, absolutely.
Yeah.
You have total creative control to override the VLM. Once the scene has depth and the materials are assigned, the system actually applies your physical action. And it uses specialized solvers depending on the material.
What does a solver actually do, though?
It basically calculates how the material should react to stress. For example, for cloth and smoke, the system uses position-based dynamics. You can think of this like treating a shirt as a net of tiny connected springs. If you pull one corner, the math calculates how the tension ripples through the rest of the springs.
That makes sense. What about liquids?
For liquids and sand, it uses the material point method, which is fantastic at handling materials that can act like both a solid and a liquid depending on how hard they are pushed.
The actions you can apply are incredibly diverse too, right? Like you can apply 3D point forces, 3D force fields, which is basically just wind, or even articulated robot commands.
Yes, you can literally drop a virtual 3D robotic arm into your 2D photo and have it grip something.
And those robotic commands are solved using inverse kinematics, according to the paper.
Yeah, inverse kinematics.
Meaning what exactly?
So inverse kinematics is a way of calculating movement backwards. Instead of telling the robot's shoulder to move 10 degrees and the elbow to move 5 degrees, you just tell the robotic hand where it needs to end up in space.
Oh, that's so much easier.
Right. The math works backwards from the hand to automatically figure out exactly how the elbow and shoulder need to bend to reach that point.
Okay, so all of this complex math, the collisions, the springs, the inverse kinematics, is happening incredibly fast, generating that optical flow weather map and the course preview we talked about.
Correct.
But here's something I don't quite get. There are pure physics-based renderers out there. Like, the source material mentions one called Gaussian.
Right, Gaussian.
So if the physics engine already knows exactly where everything is moving, why go through the trouble of adding generative AI at the end at all?
Well, pure physics-based rendering like Gaussian gets the math completely right. The object will move exactly as it should, but visually. It looks like a cheap, low-resolution video game from the late 90s.
Oh, really?
Yeah. The math engines struggle immensely to synthesize dynamic shading, realistic shadows, or complex, changing textures.
Actually, the paper shows a side-by-side example of this with a boat in the water. The Gaussian version gets the boat moving correctly, but the water looks totally flat and lifeless.
Exactly. By handing the physics data off to a generative AI, RealWonder achieves what a pure simulator struggles to render. The generative AI paints in the real water splashes, the soft folding cloth textures, and accurate lighting changes as objects move through the scene.
So it marries physical accuracy with photorealism.
Yes, exactly.
Okay, so the pipeline makes total sense. Geometry, materials, physics calculation, and finally AI rendering.
Yeah.
But there is a glaring issue here, and it is all about speed.
Oh, absolutely.
Traditional video diffusion models, the kind that make those hyper-realistic AI clips, they usually take about 50 computational steps to generate a single frame. They're incredibly slow.
Painfully slow.
Yeah, like if you flick that coffee mug on your screen, you cannot sit there and wait 5 minutes to see the result. You need to see the coffee spill right now.
And achieving that speed is perhaps the most impressive technical feat in the paper. RealWonder runs at 13.2 frames per second at a resolution of 480 by 832 on a single GPU.
Wait, 13 frames a second. Standard AI video takes forever to render just a few seconds of footage. How do you possibly condense 50 complex steps of AI video generation down to real-time speeds without the output turning into a blurry, glitchy mess?
They used a technique called distribution matching distillation, or DMD.
Distillation, okay.
Think of traditional video generation like a sculptor slowly chipping away at a block of marble over 50 delicate sequential strikes to reveal a statue. Distillation trains a smaller, faster student AI by having it watch the massive teacher AI do this millions of times.
So the student basically learns the shortcut.
Exactly. The student learns how to make the final sculpture in just 4 massive, precise strikes instead of 50.
Wow, just 4 steps.
Yeah. And they specifically trained this 4-step student model to understand that optical flow map we discussed earlier. They fed it a data set of 200,000 pairs of flow warp noise and video.
So the AI inherently learned how to follow those pixel velocity instructions instantly.
You got it. Okay, that solves the speed issue. But if I am interacting with a photo continuously, say I am dragging a toy car across the desk for 10 seconds straight, doesn't the AI eventually forget what the original desk looked like?
That is a very real problem.
Because if you just generate frame after frame after frame, standard AI tends to drift, right? It starts hallucinating weird artifacts.
Yeah, drift is a major challenge in real-time streaming. To stop the AI from forgetting the original room, they manipulated the KV cache.
Which is what?
You can think of the KV cache, or key value cache, as the AI's short-term memory. It's like a bulletin board, where the AI pins reference photos while it works.
Okay.
Normally, an AI forgets the exact details of frame 1 by the time it draws frame 50, causing the video to warp. By locking certain visual anchors from the very first image into that cache, they force the AI to remember the original structure of the room no matter how much you interact with it.
Oh, that's super smart. The source material also mentions a self-forcing autoregressive technique. Yes, that is the second layer of defense against drift. During training, they force the model to constantly double-check its own recently generated history against the original scene.
Ah, so it catches its own mistakes.
Exactly. It trains the AI to self-correct on the fly before a tiny error spirals into a massive hallucination.
The visual results of all this working together are just stunning. Like, to paint a picture for you listening, the source material shows a robotic arm reaching down and perfectly slicing through a block of butter.
It looks so real.
It does. You can see the butter deform and separate exactly as it should, with a realistic lighting reflecting off the knife. In another example, they apply a virtual wind force to a sand house built on a beach.
That one's my favorite.
Yeah, you watch the sand realistically blow away and collapse to the left, granule by granule, with the shadows shifting in real time.
The researchers actually conducted a massive human study, too.
Yeah.
They had 400 participants compare RealWonder against all the baselines, Visgasin, CogVideoX, Tora.
And how did it do?
Across the board, people favored RealWonder over 80% of the time for following the physical action correctly, having realistic physical plausibility and overall visual quality.
So what does this actually mean for you, the listener? I mean, we've talked about point clouds and distillation and KV caches, but why should you care about real wonder?
Because this marks the dawn of true interactive world models.
Okay, big statement.
It is.
Mhm.
Up until now, our relationship with generated media has been entirely passive. You
Yeah.
type a text prompt, you hit enter, and you sit back and watch what the machine gives you.
Right.
This technology shifts that paradigm entirely. It moves us from passive consumption to active participation within simulated environments.
Think about the real-world applications for something like robotics and planning. You could snap a photo of your incredibly messy garage.
Oh, we all have one of those.
Right. And before you even lift a single box, a robotic system could instantly simulate 1,000 different physical ways to reorganize it.
Pushing boxes, moving tools, testing weight distribution, all in a physically accurate, photorealistic simulation derived entirely from that one static photo.
Or consider the implications for augmented and virtual reality or gaming. Imagine taking a picture of your living room and instantly that photo is converted into a fully interactive, physics-based video game level.
Yeah, the couch cushions in the image now have real simulated bounce and weight. You could bounce a virtual ball off your actual coffee table, and the physics, the lighting, and the shadows would behave exactly as they do in reality.
It solves the ultimate what-if scenario, instantly, visually, and accurately. You don't have to wonder what happens if you push something, you just do it in the simulation.
And it bridges that gap without needing impossible data sets of invisible forces. By simply using existing physics engines as a translator, it unlocks interactive capabilities we thought were still years away.
Let's bring this all together. We started this deep dive looking at AI models that hallucinated extra persimmons because they couldn't comprehend basic mass or object permanence.
Right.
And we have walked through how the team behind RealWonder completely bypassed that problem. Not by forcing the AI to learn the complex math of physics, but by using a physics simulator as a secret translator.
Exactly. The system takes a single flat image, gives it depth, figures out what everything is made of, calculates the physics of your action using specialized solvers, and then hands simple visual instructions to a lightning-fast AI generator that has been distilled to run in just 4 steps.
Giving you the ability to physically interact with still images in real time.
It is a remarkable synthesis of 2 very different fields of computer science,
Mhm.
hard mathematical simulation and generative artificial intelligence. But as we wrap up, this raises an incredibly profound question, something for everyone to consider.
Okay, lay on us.
If an AI can perfectly simulate and render the physical consequences of any action from a single 2D photograph, how long until we can step into historical photographs? Think about it. What happens to our relationship with the past and with reality itself when a century-old still image of a bustling city street is no longer just a frozen moment in time?
Right.
What happens when it becomes a paused, fully interactive universe, just waiting for you to hit play, step inside, and push a wooden cart down the cobblestone road?
That is wild to think about. Keep that in mind the next time you look at an old family photo on your phone, or, the next time you look at that coffee mug sitting on your desk.